Ever noticed this? On a hot road trip, soda tastes flat and watery, whereas from McDonald's, it tastes insanely fizzy. It's not just the straw, it's science. Water is just H2O. Soda is water with CO2 dissolved in it under high pressure. See those bubbles? They are not just for decoration, they are bubbles of CO2 trying to escape. CO2 exists as individual molecules, not bubbles in our setup. These molecules have their own kinetic energy and move in random directions. Because of this, a constant exchange happens at the surface of the liquid. Some CO2 molecules escape the liquid and enter the gas, whereas some CO2 molecules collide at the surface of the liquid and enter it. Note that fizz appears when more number of CO2 molecules leave the liquid than the number of molecules that enter it. Note that only the partial pressure of CO2 molecules present in air matters, not total air pressure. High partial pressure of CO2 molecules in air indicates that there are more number of CO2 molecules present in the air. Now, that would mean more collisions with the surface of liquid and hence more CO2 gas stays dissolved. Temperature controls how easily CO2 molecules can stay inside the liquid. Now, this bottle is cold. Let me open it and notice what happens. Hear that? There is so much fizz. And as you can see, there are lots of bubbles forming. Now, I have a warm bottle of soda. Let's see what happens. Saw that? There is so much more fizz and a lot of new bubbles are popping up. As we saw, both the bottles contain CO2 molecules, but the warm one could not hold the molecules easily and hence gas escaped. And we saw more fizz. Temperature is the measure of molecular motion or average kinetic energy. Higher temperature means higher kinetic energy, hence the molecules move faster and escape the liquid more easily. Whereas lower temperature means lower kinetic energy, that means the molecules move slower and cannot escape the liquid more easily. What we discussed can be mathematically expressed as Henry's law. Concentration of gas is equal to Henry's constant times partial pressure. Over here, Henry's constant is inversely proportional to solubility of our gas and partial pressure of the gas is directly proportional to solubility. Now, Henry's constant depends on temperature, and as we know, lower the temperature, higher the solubility, and higher the temperature, lower the solubility. We can also say concentration of gases at low temperature will be higher than concentration of gas at high temperatures. On a road trip, our soda warms up, solubility drops, and CO2 escapes. The drink tastes flat, whereas McDonald's keeps its drink cold, carbonates it under high CO2 pressure, and serves it fast, so very little CO2 molecules escape. Cold soda isn't just colder, it's physically holding more carbon dioxide, and hence the difference is explained.